So, Minister,
Um, Good evening, students. Today is the second day of the introductory functional analysis course. We have Dr. Saurabh Mandal for this course. Uh, Now he is starting. Sir, please start.
okay, thank you. So, in the first class, mm, we see what is a metric space, and we are we have seen several examples of metric space. Now, today, we'll learn about separable metric space. Okay, so separable metric space. Okay, before that, do you remember what is a dense set? What is a dense set? If we consider the set of all real number, then what is a dense set?
Any subset of R whose closure is R.
Okay, that means a subset of R that is dense in R provided a closure that is
To R.
R. Okay. Okay. So any example?
Set of rational numbers.
Okay. So you can consider set of all rational number as well as set of all irrational numbers.
Irrational.
Okay. So same thing is true for metric space also. A subset M of a metric space is called dense provided M closure is equal to X. Okay. Now, what is M closure? What does it mean? Can you tell me what is M closure?
Smallest closed set containing M.
Okay. So that definition is for topological space. But it is actually
Okay.
M closure, that is the
M union.
union of M union with
Derived
its
set of M.
derived set. Derived set. So what is derived set?
Set of all limit points of M.
Okay. So M dash, that is the derived set of M. That means it is the collection of all limit points of M. Clear? Now, A X belongs to M dash. What does it mean?
X is a limit point of M.
But how can you write it mathematically?
Okay.
Belongs to interest. It
Uh,
There is a condition if and only for any epsilon greater than 0, if you consider the open ball centered at X and radius epsilon, this intersection F, this intersection M, clear?
Yes,
That
sir.
means every deleted neighborhood of X that intersect M. Okay. Now, so a set is dense if M closure is X. Okay. Now, what is separable space? So, if a space X is called separable if it has a countable dense subset. Okay. So, as an example, if you are considering what is the first metric space I have given in the example yesterday,
Real number.
set of real number
So,
with the metric d
Yes.
that is defined by
the
Modulus of
usual
x
modulus
minus y.
whether this space with this metric is a separable metric space.
as a countable tensor
Obviously, it is a separable metric
yes
space as q
is countable.
q is a subset of r, and with this respect to this metric q closure that is r. So R with this metric D, that means usual metric, that is a separable metric space. And instead of R, if you are considering C with the usual metric this, then is it a separable metric space?
Yes.
If you consider this set, that is A plus IB, where A and B they are
Belong
from
to the rationals.
rational numbers. Obviously, it has a bijection with Q cross Q. So it is A is a countable set, so no problem. And obviously A is dense in C. So C also C with the usual metric, it is also a separable metric space. Okay. Now, now if we consider R with discrete metric space, R with discrete metric, whether this is a hello,
Yes, sir.
if we consider R with discrete metric, so mm, whether R with respect to this metric is a separable space or not. What is discrete metric? There is a theorem, or you can say some a set M in X is dense if for any open set O in X, O intersection M, this becomes a non-empty. Okay. And you also know that every open ball This is also an open set. Now, if you consider the open set with respect to this discrete metric space, and if you consider the radius is less than 1, in that case what will you get? Only singleton sets. Okay,
Um, sir,
so that sorry.
uh, sir, intuitionally, can we say a space is separable if we can find a grid of points that is countable, no matter
Hmm,
how much we zoom in on any part of the space? Uh,
hmm,
will we always find a metric from that grid, right?
very close. But um, I can give you one uh, practical example. If you in a room, and if you use some room freshener at the corner of that room, whether the density of that fragrance at the whole room is same.
No.
If you hello.
Yes, sir.
Okay, so come back to this example first, then we will consider. Okay, so if you consider these open sets with respect to the radius half, in that case you will get only singleton set. So are with discrete metric space, every singleton is open, and if you are considering two distinct point, in that case you will get two disjoint open set. Okay, so as R is uncountable, so if some set that intersect every open wall or every open set, then A must be uncountable. So what can we say that if A is a dense in R with respect to the discrete metric, in that case A should be uncountable. So is there possible any countable set which can dense in R with respect to discrete metric? Obviously the answer is no. So R with discrete metric space, this is a non-separable non-separable
Metric space.
metric space. Okay, and which result we have used for the to prove this? Suppose a set M in X is dense if for any open set O in X, O intersection M that is non-empty. That means M intersect is open set in X. Okay, and as a consequence of this example, you can say that a discrete discrete metric space is separable if and only
The space is
Hmm? The space is
dense.
the space is countable set. Okay. Now, why the space should be a countable space? Because the only dense subset in that space is X itself. So that's why the space should be a countable space. Okay. Now remember, what is L infinity space? What was that? L infinity space?
Set of all bounded sequences.
Set of,
All bounded sequences.
that means
Uh,
collection of all xi's,
uh,
so that
we get a
xi is lesser or equal to some,
Cx. For some Cx greater than
actually
zero.
x equal to xi, and for for this x I am considering this cx. Okay. So for different sequences there are different cx's. Okay. So that means it is all set of all bounded sequences. So whether this space is separable or not, any guess?
Uh, no, no, because we cannot uh, find any countable dense subset. That
Okay, so how to prove that? And there is another note: subspace of a separable space, subspace of a separable space is separable. Okay, so now the question is whether L infinity, what is the metric D here? D of xy equal to supremum of L infinity with this metric is a separable metric space or not. Okay, so if it is a separable metric space, in that case you need to find some countable set, a countable subset, such that a a closure that is equal to L infinity if it is a separable space. Yes or no?
Yes, sir.
So if the space is not separable, then what happened?
uh,
There exists no such A that whose closer is L infinity.
So that means
we cannot.
if the space is separable, that means it has at least one countable dense subset. Okay. So if the space is not separable, so what is the negation of that condition?
There is no countable dense subset.
So if you are considering, that means if you are considering some countable subset of L infinity, in that case, A cannot be a dense subset. Yes or no?
Yes.
Or otherwise, you can say that if there exists some dense subset, then that set must be uncountable. Yes or no?
Yes.
Yes.
Or if f bar equal to L infinity, then A must
A
be
uncountable.
okay. So in the previous example, what is the method? First, we have considered open set. Now, the number of open set that is uncountable and they are mutually disjoint. So, if some set that intersect is open set, that means it has to be a uncountable set. So, we will use same trick here. First, we will consider a we will make a collection of uncountably disjoint open set in this space, and in that case if some set that intersect every open ball, yeah, and in that case a must be a uncountable subset. So what is my first motto? I have to make uncountable disjoint open set in this space first. So I'm considering some S, that is the collection of all sequences AI, okay, where AI has only one, only two options. That is AI may be either 0 or 1. Okay, so that means you are considering also sequences which are either whose stem is either 0 and 1. So obviously it is the collection of all bounded sequence. But I mean is element of S that are obviously bounded, because what
Yes,
is the
sir.
maximum? What is the maximum? Maximum to, 1, and what is the minimum term? That is 0. So is element of S that is a bounded sequence. So S is obviously a subset of L infinity. It is clear.
Yes, sir.
Yes or no? Now, if you consider the D metric on restricted on S, what will you get?
The discrete metric.
Yes, because if we consider two sequences AI and BI from S, AI equal to BI, if for all AI equal to BI, in that case AI equal to BI. If there exists only one distinct term, then these two sequences become distinct sequences. So if we are considering this D matrix in S, in that case we'll get discrete matrix. Discrete matrix. So if we consider that discrete matrix, let it is D1, say. So if we consider the discrete matrix, and if we consider the open ball centered at the sequence AI and radius half, what will you get?
AI.
So for distinct AIs, you will get distinct open balls. Yes or no?
Yes, sir.
So So this is basically a collection of disjoint open balls centered at AIs. Now the question is whether this collection become a uncountable collection or not. Now, if you consider this set S, tell me whether this set is uncountable or countable.
Uncountable.
Why? Mm,
There are
why?
there are uncountable number of uh, zeros and ones in that S.
If you consider some AI, then how many options for that means A1, A2, dot, dot, dot. How many options for available for A1?
Uh, two.
One for natural two.
That means 2 to the power n
And it has two to the power.
cardinality.
That is infinite.
That is
Oh,
C.
I'll
That
one.
means cardinality of and what is that value? It is a uncountable collection.
Yes.
Mm.
It equals to C.
So you are getting the cardinality of this collection. It is same as cardinality of S. That is C. So in these examples also you are getting an uncountable collection of disjoint open balls. That means open sets. Okay. So if A is some subset and if A intersect then A must be
Countable.
okay. So L infinity does not have
Any countable
any
in subset.
Countable subset.
Ten subset.
dense
Yes.
any countable dense subset. That means L infinity is not
Separable.
okay. But this is your homework. LP P capital equal to 1. This is separable space. Okay. Oh, one more thing. By the same trick of example 3, that is L infinity, you can prove that the set of all bounded function defined on this is a non-separable space. And I've also given the example of continuous function defined on AB, CAB. This is collection of all real valued continuous function defined on AB. So what do you think? Whether this is a separable or non-separable metric space?
If if we are taking the rational polynomials, then it must be.
And there is one well-known theorem, that Wester's theorem, that is every continuous function can be approximated by some polynomial function. So, and if you are collecting all polynomial with rational coefficient, in that case, uh, that is a countable collection, and that is dense in CAB. So CAB with that, so that collection is dense in CAB. So CAB is a separable metric space.
Sir, can I use the Wheeler's approximation theorem to prove
Yes.
that LP space is separable?
No, no, no. You don't need to that LP space. You can consider some sequences whose finitely many terms are non-zero and each term are from Q. In that case, you will get some bijection with Q to the power n, and in that way, that set is that set is dense in LP. You can prove that way in that way.
Okay.
Okay, okay. So that's all for today.
Oh, okay. Sir, I have a question. Sir, what about the Hilbert cube?
Okay, so you are asking for Hilbert cube. Okay, we can discuss it later because it need if you uh, explain it very clearly, then we need one more class for that.
Okay,
Okay.
okay, sir. Okay, okay, sir.